So last time we got to prove this theorem about the operator norm of a sub-Gaussian random matrix with zero mean entries. So independent zero mean sub-Gaussian entries. And we showed that with high probability, the operator norm would behave like this. So root m plus root n if the dimensions are m and n, and plus some t that allows you to control the probability of this event. And so we also discussed that this is a significant result. It's a little bit surprising because the operator norm in the worst case for matrices with bounded entries could be as large as, let's say, root mn. And so this is saying that with high probability, if the entries are random zero mean, then the operator norm is much smaller. And so we proved this using the discretization argument. So you discretize the variational characterization of the operator norm, which is expressing the operator norm as the maximum of these, the norm of AX, where X varies in the sphere. And so this sphere is uncountable. The set of values is uncountable, so we can't do union bound on it properly. So the idea is to reduce it to a discrete set by using the an epsilon net. And over an epsilon net, we pay a price of approximation error, price of an approximation error of size epsilon times the operator norm of A. And so once you rearrange, you get that the operator norm over this operator norm is bounded by the supremum of the same quantity over the net up to a factor which can be made to be constant. And then for this, you just have to verify or drive a concentration inequality for a given fixed x. This in fact has to be z to be correct. And then you would do a union bound. We actually did a little bit more discretization. So we did this discretization over the L2 ball as well. So you would have operator norm bounded by the maximum of these bilinear quantities over two sets of epsilon nets. And these quantities are linear combination of the elements of A, and these sums are sub-Gaussian. We can compute the sub-Gaussian norm. The sub-Gaussian norm turns out to be bounded by the same quantity that's bounding the sub-Gaussian norm of each entry due to the L2 constraint on x's and y's, which is interesting. And then using sub-Gaussian concentration, you can write down a tail bound. And then that will translate to bound on operator norm using the union bound. And then the last step is to sort of balance the sizes of the nets and the tail, exponentially decaying tail. And these nicely balance out because this is exponentially going down and this is exponentially going up as u increases, this exponentially go down, and as m and n increase, this exponentially blows up. So if you properly choose u, by say taking it to be this much, then you can cancel out this growing term and you get a tail bound, which is of the desired form. Okay, so that was last time. Any question, concern about this? So that was the result. Okay, if not, there is a improvement if you look at sorry, let's go back up here. If you look at the special case where every entry is Gaussian, standard Gaussian. So if you look at the standard Gaussian matrix, again, A here is n I believe m by n or n by n, doesn't matter. Then you can show that like with specific probability, this much probability, or at least this much probability, A is bounded by, the operator is bounded by root m plus root m plus t. So there's no extra unknown constants here. And this is a very useful result if you want to quickly check a proof or an algorithm. It's good to remember this result. If things work out for the Gaussian case, usually you can extend it to the sub-Gaussian case as well. And the proof of this result is you could prove it using a very different argument, and that argument is to note that the operator norm of A is a Lipschitz function of each, like the vector of all entries. And we discussed this when we discussed the Gaussian concentration. So in order to show that, you have to show that, for example, if I have two matrices, if I look at the operator norm, the deviation is bounded by, in fact, it's going to be one Lipschitz, bounded by, let's say, vec A minus vec A prime, L2 norm, which is nothing but the Frobenius norm of the difference. And this is the case because anyone remembers why this is the case? This is less than or equal to that. Anyone?
Is it because the Frobenius norm is like equal to the sum of all the singular values, but the operator norm is just the maximum?
Yeah, so some singularized squared, so that would be the Frobenius norm. Yeah, so the operator norm is in general, this is like the maximum of sigma I. The singular value, this is going to be less than the Frobenius norm, which is the sum, square root of the sum of sigma I squared. So operator norm is always lower bounded by the Frobenius norm, and you do an inequality here. So this is bounded by A minus A prime operator norm, which is the triangle inequality for the operator norm, and then the operator norm is bounded by the Frobenius norm. So the operator norm is Lipschitz function, so it concentrates. And then what we have to do is, so we have a very nice concentration inequality for which we also know the constant. So this is like t squared divided by, remember, 2L squared, and L here is 1. So the only thing that we have to like figure out is a bound on the expectation of the operator norm. And you could use techniques similar to the one that we discussed for controlling the RE sort of constant to find the sharp bound on the expectation of the operator norm. So you can write the expectation as, so you remember by the discussion last time, this is going to be the supremum over y in, let's say, or yeah, sup or max, it doesn't matter, sup x, y a x, this would be Sn minus 1, x in Sn minus 1. This is what we showed last time. And so this is a Gaussian process. So if you define this to be some x t, this is like expectation of supremum xt, t in t, where t is just a set of all x, y, such that x is in Sn minus 1 and y is in Sn minus 1. And very similar to the Gordon's inequality, actually, it's like a special case of this is the Slepian inequality. This is not Sudakov. Yeah, it's sometimes also called the Sudakov-Fernig, I guess. Slepian inequality. depending on which version you want, but pseudo-Covariant or Slepian is just a special case of the Gordon's inequality, special case of the Gordon's inequality. And so you could exactly compare it with the same process. If you go back to the discussion of the proof of the RE condition, you can compare this with the exact same process that we constructed. And if you repeat that argument, I'll probably post it as a maybe homework problem. Then you would get this bound. And then if you plug back in, then you would get this nice result. So you can see this is a very different argument than the epsilon net argument, because the concentration just comes for free once you realize that this is a Lipschitz function. The only thing that you have to worry about is the expectation of the operator norm. Whereas here, you can see that we did not derive deviations from expectation of A. We just directly bounded the quantity itself. And so that's why we sort of also pay a price because of the inaccuracies in this type of argument. Okay, sounds good. So it's good to remember this sharp bound. And then there is a very similar, again, by Gordon's inequality, similar bound on the infimum. So you can call it this the minimum singular value. This is the maximum singular value. The minimum singular value, there's a lower bound on it, which is going to be like root m minus root n plus d, something like that. Let's say if m is bigger than or equal to n. And then you can prove this exactly using the Gordon's inequality. What we did for the proof of that theorem was so Gordon's. The RE condition was to control this minimum eigen. Actually, we did this for the minimum eigenvalue of a symmetric matrix restricted to an L1 ball of some sort. Here, there's no restriction, and so you get some result like that. And so, for example, if m is bigger than n, I believe something like, or yeah, I believe something like that. And in this Gaussian case, you might be able to prove something like this. There's this extra constant there. But I believe this should be correct. Let me know if you checked and it's not correct. But this shows, for example, that if m is, let's say, much or like reasonably larger than n, then the A is almost surely full rank. So this is the smallest singular value. This would be like SNA. That would be bounded below from 0. Okay. Questions? All good. Okay. So now what I want to talk a little bit about is how to estimate, or how to first, they're both related. So talking about concentration of concentration inequalities and estimation of concentration inequalities. So before doing that, we'll introduce a notion which is an extension of sub-Gaussian idea to vectors. So there is this definition that for a sub-Gaussian, so for a random vector, if you consider a random vector, we'll say that the distribution is sub-Gaussian if whenever you form these linear functionals, or let's say not linear functionals, but linear combination of the elements. So you take the inner product of x with u, where u is in RD minus 1 and the norm is 1. So again, remember this is just saying that u is in RD and u has unit L2 norm. This is the sphere. As long as all these, let's say, you can think of it as one-dimensional projection of some sort. All these slices or one-dimensional projections, they are sub-Gaussian, then we say that the vector is sub-Gaussian. in which case we define the sub-Gaussian norm of the vector as the supremum of the sub-Gaussian norm of these slices, okay? And this definition sort of, you can verify easily that from this definition, any vector that has independent sub-Gaussian coordinates would be sub-Gaussian by this definition. And they can bound the sub-Gaussian norm of the vector as a constant times the maximum sub-Gaussian norms of the entries. So this is fairly easy, but the definition also includes cases where the coordinates are not independent. An example is, these are discussed in the HDP. For example, a vector that's distributed uniformly on the sphere in RD of radius root D. Okay. Here this vector, which is uniformly distributed on this sphere, is sub-Gaussian with bounded sub-Gaussian norm. So that sub-Gaussian norm does not grow. But entries of this distribution or the vector are dependent. Anyone can argue why that would be the case? Why the entries are dependent? Anyone? So consider a very simple case just on the circle. So uniformly distributed on the circle, the claim is that the vector, the two entries would be independent, would not be independent, they would be dependent. Can you?
Well, I mean, you just, like, because the sum of the squares has to equal 1, basically, once you get the value of one of the variables, then the other one is defined.
It's not defined, but yeah, so there's a bound. So this would be bounded by, let's say, this, right? Over, actually, yeah, the absolute value would be equal to root 1 minus x1 squared. So there are two cases. So if I like do a slice here, so the x2 can have these two values. If I go here, the distribution, the conditional distribution of basically x2 given x1 would be this point, these point masses. And so you can see the conditional distribution varies as you vary x1. So for example, if I condition on here, there is only one value for x2. If I condition sort of x1 on anything strictly in -1 and 1, then there are two values, and then the two values change. So the conditional distribution of x2 depends on x1. x2 given x1 depends on x1, and so they can't be independent. Okay. So if x is a normal with mean 0 and identity covariance matrix, then this is sub-Gaussian with constant norm. And if x is normal with a general covariance matrix, this would be still sub-Gaussian, and the bound would be a constant times the operator norm of the square root of sigma, or this thing would be just also operator norm of sigma, like square root. You can verify that this is the case. And in order to prove something like that, you can prove something more general, that if x is a sub-Gaussian vector and A is a deterministic matrix, then AX is a sub-Gaussian vector, and the sub-Gaussian norm of AX would be bounded by the operator norm of A times the sub-Gaussian norm of X. I used to have a proof of this, but maybe I'll sign this as a homework problem. You can just not look at the proof if you have the previous version of the slides. Try to prove this yourself. And so applying this result to I can write a Gaussian vector like x times root sigma times z, and then z would have standard normal distribution. So you apply this lemma, and you can show something like that. Okay. So I don't generally know much. So the sub-Gaussian case, the sub-Gaussian vector idea is useful if the sub-Gaussian norm is not scaling with the number of coordinates. So there are cases where you can think of them as sub-Gaussian vectors, but the sub-Gaussian norm of the vector should generally scales with the number of coordinates. And in that case, this idea is not very useful. It's very useful if you have a distribution for which these finite dimensional, not finite, one-dimensional, let's say projections or slices all have sub-Gaussian norms sort of bounded. And there are examples in the HTTP book. So for example, you could have a distribution which is uniformly distributed on coordinate vectors, or like a discrete cube or something like that. And that although every coordinate is sub-Gaussian and the vector is sub-Gaussian, then the sub-Gaussian norm of the vector is not small. So the idea is not very useful there. So I'll let you have a look in the HTTP book. So any question about sub-Gaussian vectors? Okay, so what we want to do now is, let's say I want to estimate, I should probably start with discussing what is an estimate of covariance matrix. Suppose I have data x1, x2, ... xn. These are in RD, and they're independent. Probably zero mean, let's see. Yeah, so we don't need zero mean at this point. So they're independent. If they're zero mean, so suppose we have a covariance matrix. So I mean, so they're independent. Let's say they're IID, actually independent. They're actually IID from some distribution. And we would like to estimate the covariance matrix of this distribution, okay? So instead of trying to do that, I'm going to try to estimate the second moment matrix, which is the expectation of, let's say, one of these guys, let's say xi transpose. Okay, could be, for example, x1, they are identically distributed. So the covariance matrix is related to this. The covariance matrix would be expectation of x1 transpose minus something. Anyone remembers? What will be the
I guess it's expectation of x1 transpose expectation x1. Or mu.
Yeah, the other way. Yeah, mu transpose if mu is the expectation of x1. Yes. Or you could write it in a different way, but so this part is usually not that difficult to deal with. So if you can estimate this part correctly, we can sort of correct it by this, or if the distribution is zero mean, then the second moment matrix is just the covariance matrix. So I'm going to say you're estimating covariance matrices, but really you're estimating the second moments in general. You can either assume that the distribution has zero mean for simplicity, in which case the two ideas are the same, or you can just remember that the covariance matrix can be, so you can estimate the mean rather easily, right? So you could take the average. So this is a very good estimate of mu, so I can subtract, so this would be mu hat, let's say. So you can replace it with mu hat, and I would get still a consistent estimate. So that estimating the this term is not difficult. The difficulty is estimating this one. So how do we estimate? So how do you estimate the second moment matrix? What is the natural estimator? I have a sample of size n. I'm trying to estimate this. I can call it sigma.
Just like the sample average.
Yeah, okay, so that you can think of this as the sample covariance matrix, which is the average of just these terms. Just replace this with the empirical average. And in the zero mean case, this would be the sample covariance matrix. So this is an unbiased estimator, obviously, unbiased for estimating sigma, and we have sigma at n sort of converges to sigma as n goes to infinity. So if d is constant, the dimension, same probability. So why would this be true?
Law of large numbers.
Yeah, so this is the law of large numbers. Whatever norm you want to put on the deviation, all the norms would be equivalent in the case where d is fixed. So this is some norm, and then you want to show that the probability that this is bigger than epsilon goes to 0. And this reduces to the fact that each entry is converging. So this is going to be bounded by probability maximum of sigma hat, and let's say ij minus sigma ij over ij is bigger than, let's say, epsilon divided by some constant. This would depend on d. There's an equivalence between this norm, and this is also a norm, the L infinity norm of the vectorized version. And this goes to 0 because each coordinate, if you look at by the law of large number, converges, and union bound basically, plus law of large numbers gives you that this quantity converges. Okay, so it's a little bit more than the law of large numbers because we're dealing with probably, you have to somehow deal with the fact that this is a matrix valued random variable rather than a single scalar, but you can reduce it to the fact that whatever norm you're looking at, that norm is going to be bounded by constant times the maximum of the entries. And each one, if you look at, is an average. So if I look at sigma hat and ij, it's just 1 over an x. I should, okay, maybe call this something else. K maybe. K from 1 to n. Then this would be k from 1 to n, xi or xki, xkj transpose, and so this converges to expectation of xki, xkj, which is just sigma ij. Okay. So this sounds good. So this is the classical regime, like 200B ideas can be used here and ensure that this is a consistent estimator. So sigma hat n is a consistent estimator of sigma in the classical setting, which is to say D is fixed and goes to infinity. So now what we are interested are non-asymptotic bounds on deviations like this and possibly consistency. So how about consistency in the high dimensional regime, or basically non-asymptotic bounds. I don't want to assume that n goes to infinity, D is fixed. They could both be large. They could both grow. Can I have like a bound that works for all values? Okay, that's the spirit of this course. So, and a natural norm to consider is, so in this setting, if D also could grow, then equivalence of norms are not useful because these constants could depend like severely on R, so on D. So that would change the order of convergence. So we have to specify which norm we would like to use. And often people are really very interested in considering the deviation in the operator norm, because this would convergence in the operator norm would give you convergence of eigenvalues and eigenvectors generally. So the spectral properties would converge if you have convergence in this. Or stronger version is the Frobenius norm. Usually these two are considered. And the Frobenius norm is easier to work with because it just turns into a sum of squares. Whereas this, as you've seen, there's no simple closed form solution, like algebraic closed form for it. So here we're going to focus on this, okay? And so I would like to drive a sort of concentration inequality, tail of this, control the tail. The probability that this is bigger than, let's say, some function of u, or yeah, something here, something involving t. It's not going to be. So let's say a function of n in d and t is less than some other function of n, d, and t, where hopefully this is controlled. Okay, so we would like to find bounds of this form. Okay, questions? So the problem is clear. So how do we proceed proving or obtaining concentration bound for such setup? Well, let me give you the result, then we can discuss. So the idea is this. If you have a matrix which is, okay, so there's another way of writing this. So let me just point this out. This can also be written as 1 over n x transpose x, where X just has these as rows. X2 transpose. So this is often how you collect the data in the statistics. You form a design matrix there. This side would have n, the number of samples, and this side would be the dimension. Okay, and then you can easily verify that if I form 1 over n x transpose x, this just gives me this average. So we define the covariance. So that's the covariance or the second moment matrix. And we have this, or alternatively this as our estimator. The idea is then that I can control the operator norm here by sigma squared, where sigma is a bound on the sub-Gaussian norm of each entry. Okay, sorry. Sigma squared is the bound on the sub-Gaussian, or sigma is the bound on the sub-Gaussian norm of each entry. And what I would get is a bound of this form. So if you move this here, so this would be like sigma squared times this. Then there's also a slack here, which appears there. This suggests that this quantity is sub-exponential, not sub-Gaussian anymore, because of this behavior in the tail. But you can see the probability is going to zero fast because of the presence of n. And this side also, if you ignore the delta, this is also could go to 0 if d over n is going to 0, although d could also grow. Okay, so that's the result. So for the Gaussian case, let's say you can, if you remember, or you can also show for yourself, the sigma square can be bounded up to a constant by the operator norm of the population covariance matrix. And so if I rewrite this in terms of that, this is saying that up to constant with high probability, this is controlled by. So you can take the delta of the same order as this side, and sorry about that. So the what is this? Right. So the lost the train of my thought. So the yeah. So if you take the delta to be equal to, let's say, root d over n plus d over n, then you'd get twice this, and then 2 can get absorbed in the inequality there. And what you end up having is the deviation compared to the operator norm of sigma is like the relative error. So if you want, take delta to be root d over n plus d over n. So the relative error is of this size, and let's say if we want consistency, we want this to be small. So if I want this to be less than epsilon, I would have to take, so usually, not usually, but definitely you should take n to be bigger than d up to a certain constant. And so the dominant term would be this guy. So if d over n is smaller than 1, this would be the dominant term. So this would be bounded by root d over n operator norm here if d is less than or equal to n. If d is bigger than or equal to n, then you can say that this is not gonna be small. So in order to be accurate up to epsilon, then we have to have d less than or equal to n. If I want this to be less than epsilon, I'll take this to be less than epsilon, which means that n has to be bigger than or equal to up to a constant d over epsilon squared. So I need that much sample, or that many samples to approximate a high-dimensional covariance matrix without extra assumptions, just the sub-Gaussianity in the operator norm. So to approximate it in the operator norm, I need this much samples. This is an interesting result, although the sample size needs to be bigger than D. It's interesting because it could be like, you could imagine that because the number of entries here are D squared, or in the sigma there, D squared, you might say, oh, I need to estimate each coordinate accurately, and I have D squared of them. So I need at least D squared samples. And this result is saying that no, you don't need that much, you just need as much of the dimension, which is significantly less. So instead of D squared, you need D samples. And you can imagine that there is a reverse argument showing that you can't have much less than this. Maybe I'll try to. You can think of this, or we can sort of have a homework problem. Try to come up with a simple case of a. So for example, you can think of a diagonal case, and in the diagonal case, you might be able to show a lower bound that if n is significantly less, so there might be a constant such that this is less than d over epsilon squared up to a constant, then this would be bigger than like epsilon operator. So you can't achieve consistency there. Okay, sounds good. Questions? Okay, so let's see how we can prove something like that. So I'm going to forget about the specific form of the bound. I just want you to help me like outline a plan for the proof. So how do we obtain a result like this, given the things that you already know? So what are some techniques that we can use here?
Well, we're trying to bound the operator norm, so we probably want to discretize. Okay,
great. So can you maybe like specify, make it more specific? So what is the formula that I can use here for the operator norm? So suppose I have a symmetric matrix A. In this case, there's a slightly better version of the operator norm. So I don't need to do that double discretization. There is a way of writing the operator norm. So in general, you would write something like max over x, max over y. In this case, Sn minus 1, Sn minus 1, y ax, right? So this is generally true. But if A is symmetric, I can simplify this. How do we simplify it? There is a slightly better way. You guys remember?
Max over x off x transpose ax.
Can you say that again?
Max over x, where you have x transpose ax.
Right, okay. It's almost correct. There's like a little max over x, Sn minus 1, x transpose ax, which is just x inner product ax. So you can take x and y to be the same. So you can only work on the diagonal of this quadratic form, but you need to have like an absolute value here. It's important to remember that. In this case, if I flip the sign of x, this is not going to change. But the operator norm sort of if A is negative definite, X transpose A is always less than or equal to 0, or strictly less than 0. And so you end up with a negative value for the operator norm. So you need the absolute value. So this is important to remember in this case. In the case you have the X and Y, you don't need that because, or you can imagine, like, think about it. You don't need to put absolute value. You can put absolute values, but it's not needed. Here you need it. Okay, so how do we discretize now? So what do you think the discretization would look like? So this is bounded by I think I probably have this somewhere here. No. So you just discretize X. Then the question is that what is the extra factor that you pay? See if we have it here somewhere. Okay, we don't have it, but this is going to be 1 minus. Most likely, I believe it's going to be still 1 minus 2 epsilon. It could be 1 minus epsilon. Right? Not sure. But just verify this should be correct. But I could divide by something better. I don't recall exactly. But something like this would hold. X transpose AX, where N is an epsilon net for Sn minus 1. And so we take epsilon to be 1/4 as before. This would be like 2 max, and then N is a 1/4 net for Sn minus 1. And we saw that the cardinality of N is bounded by 9 to the N. Okay, so the probability that the operator norm is sigma hat N minus sigma operator norm is bounded by T is less than the probability, let's say 2T if you want. Probability that the max over X in N, X transpose AX is bounded by T. Okay, that's this inequality here. And so now what? What can we do? Oh, this is not A, sorry. And I probably should use U because X is confusing. So U is like a dummy variable. U transpose sigma hat and minus sigma U probably bigger than T. Okay. So now what? So by the union bound, this is going to be bounded by some U in N as usual. The probability of one of these, right? And usually you just do like N times the max. These are not necessarily the best bounds, but usually it works. So that's standard steps so far. So now I have to control this quantity for a given fixed U, max over U in N. So for any suffix U in N, how do you control? This probability, U transpose sigma hat N minus sigma. Oh, we have something in the chat. Oh, union bound. Yes. Okay. So that was the step that we did. Yes. So now how about this? So we have fixed U. How do we control this? While you think, we can expand this a little bit. So sigma hat n is just 1 over n, I from 1 to n, xi transpose, right? So how can we expand this? U transpose sigma hat n u minus U transpose sigma u. Okay. So this term is the expectation of the other term. Is this true? Anyone?
Yes, because sigma hat n is unbiased, and then you can just pull out the U transpose and the U.
Right. Okay, good. Yeah. So this goes in, and this is just sigma. So that's expectation. So we're dealing with a quantity minus this expectation. So this is a very good candidate for concentration inequality. So you'd expect that hopefully this concentrates around its mean. So I can simplify this expression then. So this would be, if I expand, you'd get U transpose 1 over n sum I from 1 to n, xi transpose u, which is just 1 over n sum I from 1 to n, U transpose xi, and then xi transpose u. And these two are just the same because things are scalar here. And if I transpose one, I get the other. So they're equal. These two are equal. So what I would get is that this is going to be equal to 1 over n sum I from 1 to n U transpose xi squared, right, minus the expectation of the same thing. And because things are linear, I end up just having that this is U transpose xi squared minus the expectation of U transpose xi squared. Okay. So this is good because we have reduced things to averages of independent random variables. So whatever this is the expectation of that random variable. And so we have to figure out the properties of this. So we know that, remember that xi's have independent sub-Gaussian rows. So so here, this is a sub-Gaussian vector, right? So the vector that we introduced, it's not like the entries of xi are not necessarily independent, but as a vector, it's sub-Gaussian, and sigma is the bounded sub-Gaussian norm of this as a vector. Okay, so now given that information, what can I say about this object? Well, actually, what can I say about what is the tail behavior? U transpose xi. So recall that xi is a sub-Gaussian vector.
It's sub-exponential because it's like the products of sub-Gaussians.
Yeah, I was asking for something simpler. So this is sub-Gaussian.
Oh yeah.
Right. Because of the definition. So we have the definition here So this is a U transpose X. X is sub-Gaussian vector. So U transpose X is, and U is in SD minus 1 here. It's, as we discussed, this is a net, and is a net. So U belongs to a net, and the net can sort of be restricted to the sphere. So this is sub-Gaussian, and then as Naveen pointed out, this square would be sub-exponential. So you can see where the sub-exponential tail bound comes from. So that there's a quadratic form involved. You can either say that it's a product of two sub-Gaussians, or you directly compute it. In fact, there was a result that I could directly compute the sub-exponential norm of this in terms of the sub-Gaussian norm of the other guy. So what would be? Anyone remembers this result? Say sub-Gaussian norm of this to the power 2, right? So we know that this is bounded by sigma squared. So sigma squared is a bound on the sub-Gaussian norm squared of the vector, and so it bounds all these slices, sub-Gaussian norm, all these slices. Okay, so then what? So we have that every entry here is a exponential random variable. They're independent, and you're subtracting the mean. So this is a zero mean sub-exponential random variable. So what kind of tail bound do you know about these objects, or for these objects? The probability that this is, so I'm gonna write it as ZI. So we care about the absolute value, in fact, right? So I care about the absolute value. So if I call this, this whole thing, call this whole thing ZI, then I have the absolute value that's bigger than T. ZIs are sub-exponential zero mean, and sub-exponential norm is bounded by sigma squared. Let's see. What can we have here? What kind of concentration inequality do we have? Let me remind you. So we had sub-exponential variables, and we have the Bernstein type inequality, or that was a 2-parameter formulation. That's the result of used here. And this is the kind of bound in terms of the psi1 norm, or sub-exponential norm we would expect. So these are like different versions of the Bernstein for sub-exponential variables. So we're going to use this. This is exactly the setup. So XRs are independent. So here it's like ZIs are independent, zero mean sub-exponential, and the sub-exponential norm of each one is bounded by sigma. So what I end up having is just replace this with sigma squared and this with sigma. So that's the result that I'm going to get, right? Okay, this is like, people remember this result. Oh, I see another chat. Right, okay, so Evan mentioned the Bernstein. Sorry, I usually have a delay looking at the chat. Yeah, so that's the Bernstein. So that's how there's this n here. So you're looking at the average. So let's go back here. So the result that we get is that this is bounded by 2 x negative, that's some constant, times n times the min t squared or sigma squared plus, or and T over sigma. Oh, actually, this is not correct. So this is going to be, so that K, let's go back here. This has to be covered for. This is going to be sigma squared. So not this square. So the psi 1 norm would be bounded by sigma squared. And so what you would get is, this is the tricky, a little bit tricky, because if you remember, the psi 1 norm is the psi 2 squared, so this is bounded by sigma squared. So this is going to be K squared. So here, Bernstein, say corollary 1, sorry. Corollary 1 with K equals sigma squared. So I get sigma to the 4th and then T over sigma squared. Okay, that's what do we get? And so if I replace, so this holds for any t bigger than or equal to 0. Now let me replace t with sigma squared t to simplify. Then I would get the probability that 1 over n summation I from 1 to n zi bigger than t is less than or equal to bigger than sigma squared t. Right? Is less than or equal to 2x negative c n min. This is just going to be t squared, and this is going to be this t. Okay, so you get the sigma squared here. And this is nothing but, the way that we define it, this is nothing but this guy. So we have, this is just u transpose sigma hat n minus u. Okay, questions? So we had the result that we wanted. So we have a control over this, uniformly over u, so there's no u involved in the bound. So I'm going to just copy this. So this bound, copy, paste. Okay, so we had the bound, right? And now I just replace things with, I'm just going to do this instead of this. I would get 2 sigma squared t. This would be sigma squared t. And then I have a bound on this. So this is going to be, this is 9 to the n, and then e to the negative c n times min t squared and t. Okay, so we're almost done. So what will be the next step? So let's compare what we have here. So we're a little bit off. Why are we a little bit off? Because I'm missing this piece, right? And also, so you're missing the D here. So where does the D come from? No part of this argument shows D here, right? So is this correct so far? People think this is good. Did we make any mistake here? Okay, so let's go back to the proof. Okay, so there is something that we missed, and that's this part, right? So this is not 9 to the n. This is 9 to the d, because we're dealing with, this was the mistake that we made. These are d by d matrices. So if you take A to be sigma hat n minus sigma, then you would have to discretize the d-dimensional cube, so you'd get 9 to the d, and the rest seems to be fine, okay? So I would get the d involved here. Now I'm going to use a trick, which is, it's not a trick, but there's a very useful lemma that you can translate between the tail and the probability of the tail bound, using this fact that if I look at these two functions, so minimum of t squared and t, if I set it equal to delta squared, then t would be equal to the maximum of delta and delta squared. And if you plot these two functions are basically the inverse of each other on 0 to infinity. Okay, so I'll let you figure this out. But this is very useful to remember. So if I want to, so at this point I want to get rid of this, but this sort of complicates how should I choose t. I'm going to move the complexity of this to this part. So what I'm going to do is, so move the complexity of min t squared to the other side. So take delta squared to be min t squared and t. This would be the same as t would be max delta and delta squared. So if I do that, then I would get probability that sigma hat n minus sigma operator norm bigger than or equal to 2 sigma squared max delta squared and delta is bounded by 9 to the d times e to the negative c n delta squared, right? So this is delta squared. So bound simplified, okay? So that's the little trick. Now I can take, I'm going to replace delta with, so I want to kill this, and there's an n here. So generally you want the, basically, n delta squared to be of the order of d. So if you set n delta squared to be of the order of d, you'd roughly get that delta has to be root d over n, you see, to be able to kill that. And I'm going to be a little bit more, so I'm going to change delta to, I want another slack here, so we're going to define a different variable, but I'm just going to change it to d plus n. I'll leave the slack there. So if I change it to that, what I would get is 9d e to the negative, let's say c1 times this. So you get the c and then c1 n and then delta plus root d over n squared, and this is going to be bounded by 9 to the d e to the negative c c1 n delta squared plus e over n, and I just dropped the cross there. And so you can see it's going to be bounded by 9 d times 1 minus c c1 and then e to the negative c c1 and delta squared. So this times this, and by taking c1 large enough, this can be made less than or equal to 1. So you can make the power negative, so you can get rid of the d here. So I have the right tail. So what remains is what happens to this guy when I do that. So you get 2 sigma squared. I'm going to bound it by, the max is just bounded by the sum because they're positive. And so what I end up having is C1 delta plus root d over n squared plus, I'm replacing delta with C1 delta, I remember. So C1 delta plus root d over n. This was not necessarily the best. So we could call it delta tilde if you want. So that to avoid confusion. This would be delta tilde. And then so you'd extend, you'd get C1. So I'm going to also absorb the C's into this. So you'd get another C2 sigma squared. Delta tilde squared plus delta plus d over n plus root d over n. Okay. Does this sound good? So I'm just replacing the max here with the sum and plug in this value and then ignore the constant. So once you do this, the result will look like this. So if you haven't made any mistakes, so we prove something like sigma hat n minus sigma operator norm bigger than C2 sigma squared delta tilde squared. I'm going to rearrange a little bit. Root d over n plus d over n plus delta tilde over 2 plus delta. And I'm going to actually do this. I'm going to this is bounded by, let's say, C3. This is bounded by twice the maximum. So I just replace it with the maximum. Max delta 2 and delta plus the rest. So I'm just going to do it here. So I'm going to change the this to C3 and just replace this with the maximum plus the max delta 2 and delta. This is less than or equal to e to the negative. There's a 2 here somewhere. So let's say 2 e to the negative. I'm going to call this C4. Okay, C4 n delta squared. Okay. So what would be the last step to get it to look like this? We have a delta here and the min here, right? I'm going to translate back. So I'm going to call this, mu delta. So, I mean, you can call it something else so that it's not confusing, but that's fine. So let delta be, this is a new variable. Dummy, these are all dummy variables. So I'm going to let it to be like that. Then delta tilde would be the minimum. So I translate back to the like put the complexity back into the probability bound. So that would be this, something like that. So I get the probability that sigma hat and sigma operator. So this last part is a little bit technical. It's not that something interesting, but to get it to the form, the above bound is equally like good. So this bound is very well. I mean, you can also leave it like this. Actually, I might prefer it that way, but in order to get it to look like what your book has, then I would get delta here. So this is delta, and then this is 2 e to negative C4. There is an n here, and then min delta and delta squared. So that's the final bound that we have in the here. Okay. Oh, sorry, you ran over time again. I lost track of that. But thanks for staying around. So that's the proof, right? Questions? So this last step was a little bit tricky, but there's no, the same idea applies. So you're just trying to choose t such that you get rid of this, and you can see that roughly t has to be of the order of n root d over n. And then there's like a little bit of work to also get a delta here, which allows you to have a slack there. But go over this, and if you have questions, we can go over it next time as well. Okay, thank you guys. Sorry we went over time, and see you next time. Okay.